Hi students, welcome to my lectures on chemical reaction engineering. In today's lecture, we are going to find design equation for a constant volume batch reactor. Yes, that means constant volume in the sense there is a fixed container in which we are putting some reactants, allow the things to get reacted, and after certain point of time, what is the remaining reactant in the reactor? Based on that, what is the conversion? Okay, that means example for maybe 50% reaction or 50% conversion, how much time that is required? Like that, we have to find out that particular equation in which we can able to find the time for 50 or 60 or 70 any conversion, right? And after this design equation derivation, we are going to solve one problem. Okay, let us go to the board. Here is our batch reactor. It's constant volume batch reactor. Before the reaction and after the reaction, volume will not change. That is why V equal to V0. V is a final volume and V0 is the initial volume. Na is the number of moles of A that is remaining after the reaction. At time t equal to 0, that is just before the start of the reaction, what are my moles? That is nothing but initial moles Na0. That is nothing but initial concentration Ca equal to Ca0. What is my initial conversion before start of the reaction? 0. That means all this at time t equal to 0, Na equal to initial moles, concentration is equal to initial concentration, conversion equal to 0. After certain time t, my final moles equal to Na, final concentration equal to Ca, and final conversion is X. Okay, these are my initial background. So ultimately we have to find out the time required for given conversion. To do that, to design of any reactor, you have to do mole balance. That means how many moles of reactant are going inside, how many moles of reactants are coming out of the reactor, and how many moles of reactant is getting consumed, or how many moles of reactant will be generating. Okay, if you do that, okay, then you get a mole balance. To design any reactor, the starting point is the mole balance. Okay, that's what the lecture starts with the initial basis. That means what are the initial conditions and final conditions, followed by the mole balance. In general, the mole balance is because this mole balance is applicable for any reactor. That means if I am talking about mole balance, on what molecule you are doing mole balance? Is it you are going to do mole balance on the reactant, or you are going to do mole balance on the product? Anything is fine, but in general we go with mole balance with the reactant, right? The reactant which is A. So you have to look into the A only. How many moles of reactant A going into the reactor, how many moles of reactant A coming out of the reactor after the reaction, in the reactor how many moles of A getting formed or generated, or how many moles of A is getting decomposed, or how many moles of A that is accumulating inside the reactor. This you have to look in terms of molecule A. Okay, because here my molecule is the reactant. A reactant means during the reaction it will get consumed, it will not get generated. Okay, that is why during our mole balance we make few terms equal to 0. So let us do the mole balance on A, which is my reactant. How many moles of A is getting into the reactor? That means anything that is helping the A, that is positive, anything that is removing the A, that is negative, and left is remained, that is accumulation is, that is how many moles are coming in and how many moles are going out, rest is getting accumulated in the reactor. Okay, anything that helps is positive, anything that that is consumes is negative. Keep this in mind. So if moles are coming in, the first thing is moles in per second. That means you have to compare with second, because somehow we have to get the time term, right? So mole balance has to be done in terms of with respect to time. How many moles of A is every second going into the reactor minus how many moles of A that is coming out of the reactor every second. That is, coming out means it is negative. Anything is generating or towards the reactor is positive, coming out is the negative, plus moles is generating in this reactor. Example, if moles are getting formed, right, that is positive. How many moles of A is getting generated per second minus how many moles of A is consuming per second. So in, out, generation, consumption. So the balance means get accumulated inside the reactor. That means the final, which is equal to moles of A accumulated every second in the reactor. Example, 3 moles of A, example 10 moles of A is coming into the reactor, 5 moles of A is coming out of the reactor, 3 moles of A got reacted in the reactor. So what is remaining is 2. That means 2 moles of A is accumulating in the reactor every second. So that's what the things accumulation means. So let us come back. Here there is a very simple sense. Anything, that means the entire mole balance I can represent with simple equation. Positive minus negative is equal to left. Okay. Anything that comes in is positive, anything that is going on is negative, and that is left is remained in the reactor. So positive minus negative is equal to left. And in this mole balance, which one is positive? This is positive into the reactor, this is positive generation, and these are the 2 positive. What are negative terms? Moles that is coming out of the reactor and moles that is consuming in the reactor because of the reaction. So these 2 terms are positive, these 2 terms are negative, and the remaining is accumulating in the reactor. This is the very simple mole balance you can remember. If you remember this, positive minus negative is equal to balance, that is left, or as you can see, balance is accumulations, right. Let us look into the reactor. Now you know the mole balance. Now you apply this mole balance to the batch reactor, constant volume batch reactor. So is anything in the batch reactor means reaction happens inside. You are not putting, there is nothing that is going in every second because everything is closed here. So there is no moles of A every second going into the reactor, there is no moles of A coming out of the reactor because the reactor is closed, right. That is why the first term will be 0, because every second not reactant is going inside, not every second anything is coming out of the reactor. Moles generated, I am talking about the mole balance of A. A is my reactant. Reactant always getting consumed. It will not generate because of the reaction. Because A is my reactant, example B is my product. Always the A is getting reacted. So the generation of A is 0. That means first 3 terms are 0. For this moles accumulations per second, consumption per second. Of course, which the A is getting consumed comes from the multiplication of the two terms. One is rate of disappearance of A into volume. Why? Because the rate of disappearance of A is the unit have mole per liter per second. Volume of the reactor has liters. Liter cancels, then remained is moles per second. That means moles consumption per second is nothing but rate of disappearance of A, which is minus Ra into volume. Okay, this is V. Now I know substitute 3 in 2. Moles. The time. The integral Ca to Ca0 dCa by minus Ra. This is in terms of moles Na, this is in terms of the concentration. Now the another thing you might come across in terms of conversion. Now let us change these equations in terms of conversion. To change in terms of conversion, you need to fix the order. What order reaction is happening in the reactor? If you know the what order reaction that is happening in the reactor, then for first order, consider the reaction happens in the reactor is the first order. Ca equal to Ca0 into 1 minus x, you know from the stoichiometry. If you differentiate this equation, dCa is equal to minus Ca0 into dx. And I know Ra, minus Ra is equal to first order reaction, Kca. Ca is nothing but Ca naught into 1 minus x. Now put 7 and 8 in equation 6, okay, in 6. In place of dCa, substitute this, okay. In place of Ra, you substitute Kca0 into 1 minus x, okay, that is what we have taken, right. Limits at Ca, that means at time t equal to t, Na equal to Na, Ca equal to Ca, x equal to x. At Ca, that means final concentration after the reaction means certain conversion x. That means the limits, you can see the limits. Ca, that means x, Ca0 is nothing but 0. Means Ca0 means initial concentration. That means before the reaction, the initial concentration is Ca0, at that time the conversion is 0. After the reaction, the final concentration is Ca, at that time the conversion is x. So that is why 0 to x minus Ca0 into dx by Kca0 into 1 minus x, negative symbol is there. So if you want to make this expression positive, interchange the, flip the limits. T equal to 1 by k 0 to x dx by 1 minus x. I know integral dx by 1 minus x is nothing but ln 1 minus x into minus 1 at the limits 0 to x. That means t equal to 1 by k into ln 1 by 1 minus x. That means you can also you can use this equation to find time or this equation to find time. For the first order you can use this equation to find time. So that is what the summary. You can find time for given change in moles, for a given change in concentration, for a given change in conversion. Okay, you can, that is, these two are generalized, that means it can applies to any order, especially this in terms of conversion it applies only to the first order, because here we have assumed the first order and proceeded with the derivation. So let us solve one example based on these three equations so that you can get a more clarity. Yes. Let us solve the example so it will be more clear. Estimate the time required to reduce the concentration of the reactant A from 50 mole per liter to 25 mole per liter in a batch reactor of volume 2 liters. The rate constant of the first order reaction is 0.1 per minute. That means they have already provided you the initial, that means before the they have to reduce the concentration of A in the reactor 50 mole per liter to 25 mole per liter, and to do that how much time it is required in a batch reactor. So let us tackle the problem by given data. So I know Ca0 given 50 mole per liter, Ca is equal to 25 mole per liter. Because it is a constant volume batch reactor, final volume is equal to initial volume equal to 2 liter, and rate constant of the reaction is 0.1 per minute, and initial moles, if you know the initial concentration you can know the initial moles, that is initial moles is equal to initial concentration into volume, which is 50 times 2 100 moles, final moles is equal to final concentration into volume, which is 25 into 2 50 moles, and you know the conversion. Ca0 minus Ca by Ca0, 100 minus 50 by 100, this is 0.5. That means it is a time required for the 50% conversion, you have to find out time required for 50% conversion. So it is given first order, minus R equal to Kca, Ca equal to Ca0 into 1 minus x, dCa is equal to minus Ca0 into dx. If you keep this as a given data, solve the problem using three formulas. One is with respect to moles, second is with respect to concentration, and third is with respect to conversion. And if you see, this is the time with respect to time with respect to moles. We know the formula T equal to integral final mole to initial mole into dNA by minus RA into V. I know minus RA equal to Kca into V, Na to Na0. What is Ca? Final concentration is equal to moles by volume. Okay, Na by V. This V got cancels out, K is a constant, it comes out of the integration 1 by K into integral Na to Na0 dNA by Na. I know integral 1 by x dx is equal to ln x. So this will become 1 by K into ln of Na to the limits Na to Na0. That is nothing but 1 by K into ln of Na0 by Na. So this is the final equation. Now you substitute the known values, then it becomes 1 by 0.1 into ln 100 by 50, which is equal to 6.93 minutes. That means to reduce the moles from 100 to 50, it takes 6.93 minutes. Okay. Let us do the same problem in terms of concentration now. Now the formula T equal to integral Ca to Ca0 into dCa by minus Ra. Minus Ra I know Kca. Then K comes out of the integration and integral Ca to Ca0 dCa by Ca integral 1 by x dx, 1 by K into ln Ca up to the limits Ca to Ca0. That means ln K 1 by K into ln Ca by Ca0. Now you put the known values. K is 0.1, Ca0 is 50, Ca is 25, again you get 6.93 minutes. Let us solve the same problem using conversion. For first order, we have derived the time is equal to time required for a given conversion 1 by K into ln of 1 by 1 minus x. That is nothing but 1 by 0.1 into ln of 1 by 1 minus 0.5, which is again equal to 6.93 minutes. So, whichever may be the route, that means through moles you can able to find out the time, through concentration you can able to find out the time, through conversion also you can able to find out the time. Okay. Hope you have understood the design of a batch reactor. Okay. Let us meet up with a new lecture. See you.